we are going to change topic. And now we are going to talk about oscillators. So oscillators, also circadian clocks, so clocks with a rhythm of 24 hours, and chronotherapy, which is how to integrate those 24 hours into clock therapy. So the outline of those actually two last lectures will be as follows. So today we are going to talk about the oscillators, so what do I call an oscillator and how we can actually model them using different dynamical systems. And I will show you two examples of models of the circadian flux. And tomorrow we'll see how these oscillators can influence the modeling of the lactic APD. So that's number 2. And how the modeling can help the clinicians to deciding about the best timing to give the drug at. And the third point here would be about a pump, which is a drug device to administer the drug automatically. And I will show you how we can use a PD/OD model to optimize this device. So let's start by point number 1. So oscillators are basically present in many systems. Okay? So oscillators are just systems that display this type of shape where you have a pattern that repeats itself all the time with a typical time T. So the T is the smallest duration of the repeating pattern. So we all know plenty of different rhythms. Okay, you have if the pattern is a year, we call it seasonal rhythm. If the period is a day, we call it circadian rhythms. If the period is few hours, we call it ultradian rhythms. And actually, a nice oscillator with a 24-hour rhythm is the cell cycle. So remember, we have already talked about cell cycle. And just to show you how it looks like under the microscope, I'm going to show you a small movie. So we are looking at cells in the microscope, and basically there are two reporters, red and green, and when they superimpose they become orange. And basically you will see how the cells just continue growing, and if you actually track one single cell and then the daughter, you can actually see an oscillator. So let's see. Okay, I will play it again, so try to track, maybe just focus on one particular cell. Okay, one more time. Okay, as you can see, you basically go red, green, orange, red, green, orange, red, green, orange, and then it goes like this until something stops from the outside. So that's typically an oscillating behavior. And this is actually possible to model this using a dynamical system. So I'm going to show you a very simple. Okay, let's see. So I will start with first of all a few definitions, really quick. So again, let's take the same framework as the one I defined in the first lecture. So we have a dynamical system, so x dot equal f, and so basically, so you are again in a context where you have a unique solution, provided that you have an initial condition, and you can define a very big orbit as a solution x that we have this that would be periodic in the sense that x of t is equal to x of t plus capital T, where capital T is the minimum length that actually repeats itself. So that's period. And basically, if you do have such orbits, which are actually depicted in blue here, and if these orbits attract the trajectories which are close to it, it's called the limit cycle. So if it attracts them in t equal plus infinite, so at infinity, sorry, plus infinity, it's stable, sorry. And if it attracts the trajectories at t equal minus infinity, it's unstable. So those plots are in 2D, so are for n equal to, and this is in the phase plane. So if you set n equal to, so your parameter, state variables are just x and y. And if you have a phase plane like this, you may have a limit cycle like that. And basically, if you start around here, let's say that you have a stable limit cycle. If you start here, then you will be attracted by in that shape, you will be attracted by the limit cycle. And then once you are on the limit cycle, you will stay in there. And if you look at the time dependent profile, you will probably see something like this, more or less, I guess. And from this, basically, you are on the limit cycle, and you will stay there until something else happens to the system. So let me give you an example. Which is called the Oscillator. So how many of you know the system? Nobody? Oh, yeah, two. Okay. So you have the four relations that you can see here. And we are going to track dynamics of x and y. Because as you can see, basically A, B, C, and D are either sources, A and B are sources, and C and D are what we call sinks, so basically the matter that goes in C and D is lost. So we don't need to track those four variables to be able to describe the dynamics of the system. So if you just assume that all this follows the law of mass action, you can write the equations which are here. I guess that's easy now for you. So you have these equations. And it would be handy to actually find the dimensionless forms of your dynamical system. So this is something that was already seen in, I think, the last lecture of Tuesday. So you write dimensionless equations by scaling your state variables. For this case, it's going to be like that. So you just scale your variables and put all this into your equations, and you get these equations. So now you have two state variables, x and y, and the idea is to look at the phase plane of this dynamical system. So if you want to compute the null lines, you just put this equal to 0 and that equal to 0, and you get those equations. And if you draw them, you have them. So you have the x incline here, the blue one, and the y incline here, the red part. And next, what you can do on the phase plane is actually drawing the vector field of your system, so which is the flow, so those are the arrows that you can see here. And the way that you can, so the formal definition of the vector field is just x dot and y dot, yeah? And basically what you can guess, or not guess, but just compute the direction of your arrows by looking at the sign of your derivative. So for instance, here in this area, what I will write. that's the X naught line. So on the line, X dot is equal to 0. That's the definition. And then you have the Y naught lines. So you have actually this, as well as that. So, yeah, not related to that word. More about this. Okay, so now I can look at my derivative. So basically what you can see is that if you take this blue curve, basically the xy is negative below this blue curve and positive the x dot. Sorry, the x dot is here negative, and if you cross, it's going to be positive. So if so it's going to be positive around here. Oops, yeah, that's it. And as you can see here, we actually have 4 different regions. So we have these regions here, okay? Then we have this one, we have this one, and we have this one. So if I just care about x dot, I forget about this red curve, I can then compute my x dot, or the size of my x dot for all 4 zones. So here is going to be negative, and here. Vous avez des secteurs. Okay, so let's do the same for y. So here you have another line, and basically you have xy that is positive here. So in that region, how is it going to be? Positive, okay. And now we cross the red line, so here, negative. That's B, and negative. Okay, and now you can basically guess your flow, because your flow is just this vector. So now you can say that this is going that way and down. So you can say it's going here, like that. Here you can say that it's going basically like that. Here you can say that it's going like this. And here you can say that it's going like that. And what do you think is going on? Yeah. As you can see, we are going round and round. Okay, let's try to demonstrate this. So now that I have talked about the null lines, I need to talk about the steady states. So steady states can be seen when the null line proceeds. So here there is only one steady state, which is here, and which occur at a particular point in A and B, which is 1 and B divided by 1. So the fixed point here is at 1 and B divided by 1. So this is 1 and sorry, B divided by 8. Okay. And as an exercise, which I guess you can do by yourself, you can actually show using the Jacobian and the eigen values of the Jacobian that the equilibrium is stable when B is below A plus 1 and is actually unstable when B is over A plus 1. So you can show this as not very difficult. So for the following, I need two definitions, or one definition and one theorem. So let's talk about, very briefly, so we need the definition of what is an invariant region. Sometimes it's called trapping region. And this is just a region, so a connected domain, where the flow is only pointing inwards. Okay? So basically, if you are here in 2D, you can draw any connecting domain with the flow pointing inwards. And the funny thing, I don't know if it's funny, but the thing is that if you do have inside this invariant region, so that's an invariant region, sometimes it's called the trapping region, because basically once you get into this area, you stay there, you are trapped. And imagine that you have a small hole here. This is okay. You can still have, if you have a flow like this, this is still a trapping region. And actually, if you reduce that to a single point, you get something like this. And this here, if you have an unstable equilibrium, this is still a trapping region because your flow is still pointing inward. So all these would be examples of trapping regions. And then we need a theorem, so the Poincaré-Bennigsen theorem that says that basically if the trajectory is bounded and it does not contain an equilibrium point or approaches one at t tends to infinity, then it is either a periodic orbit or it approaches a periodic orbit for t that is going to the infinity. So in practice it means that basically if you construct an invariant region that does not contain a stable steady state, it does contain an unstable steady state, just like the example I just gave you, then basically any point on the parallel is right to such a trajectory. And so the idea is that then the system will admit a periodic orbit. That's the idea. So we can apply this to the oscillator. So I'm giving you the answer, but I guess you can also construct by yourself the invariant region. And well, actually, this is an exercise to actually construct the region. I'm just showing here the results. So in blue, you have the trapping region. As you can see, the flow is indeed going inward. And in the middle, we do have the steady state. And basically, we need this steady state to be unstable so that there exists a limit cycle inside this blue region. And this is basically, if you use the Poincaré-Bennigsen theorem, you can actually say that there is a limit, periodic orbit. So when the steady state is unstable, which we know, or you are going to prove in the exercise, that this happens when V is above 8%. So basically, so you have this behavior, which is what I described here in the first dot. So then, when you continue, so when you change the value, for instance, of B or of A, you will then arrive to B equal A plus 1. And at this point, the system will actually undergo a bifurcation, which is called an opt bifurcation, because the steady state will become stable and the limit cycle will disappear. And then the system will only admit one stable steady state. And this is what happened here when V is below 8 plus 1. And just to show you how it looks, so here we have so we have three different graphs in one. So this is where you have a limit cycle. This is where you have a stable equilibrium. So this part of the curve here, this phase, is the phase plane. And here you have the x with respect to time, and here you have the y with respect to time. And basically, as you can see, whenever you have a limit cycle here, you do have oscillations in x and y. On the opposite, when you have a fixed stable point for different values of b and a, you have constant values at steady state for the system. The pointer, I will not see the pointer, c'est un peu yeah. Okay, so again, limit cycle here, phase plane will be that phase or phase, and then here you will have x, and here you have y. So oscillations in x and y when you do have a limit cycle. So b is above a plus 1, and when b is below a plus 1, you have a steady state here. That's the dot that you can barely see here, and you have constant solutions for f, y, etc. And in between, you have what's called an opt bifurcation, which was already seen this slide by Mona, I think, no? Or do you remember? So maybe I actually show the opt bifurcation on Tuesday. Okay, so this is the first example of a simple oscillator, a simple simple dynamical system. So now let's go to something that is a bit more relevant to biology. So the idea is to go into the 24-hour rhythms. So we all have 24-hour rhythms. So for instance, if I draw my activity, so this is wearing an Apple Watch or a Fitbit or any type of device you want on the wrist, and then this will record the acceleration of my wrist. And basically what you can see is that, of course, we do have activity during the day. So here yellow is the day, and during the night, hopefully for you, you are simply sleeping, so you are not active. And this is something that actually continues and repeats all days. In the body, actually, it's not just the activity. If you measure, for instance, the temperature, you can see that the temperature also follows the rest activity rhythm. And it's not just the temperature. Maybe you have heard about the melatonin. So the melatonin is sometimes we call it the sleep hormone because it's the hormone that actually peaks when you go to bed. And maybe some of you actually take some melatonin because you can actually take melatonin just before going to bed to help falling asleep. And you can also take this when you have jet lag to help recover from the jet lag. Okay, so we do have a rhythmic organization, and we know at least few things about this organization, and this is called the circadian flying system. So again, circadian is for 20. So it's like this. So maybe you don't have to get all the information, but the idea is that basically in each cell of the body you do have a clock. So this is a zoom on a cell, and you do have a clock, which is a type of oscillator, just like the one we saw with the oscillator. And then this oscillator will induce other oscillations to other cell functions, which for instance could be cell cycle. I mean, the clock is actually linked to the cell cycle. So this is an autonomous oscillator. This is important to understand that if you take the cells, and actually you can do that, if you take the cells and put them outside of the whole body, it will continue going round and round as an oscillator. And one cell for one oscillator, and then of course you can have coupling of the oscillators for the different cells, but this is another topic. And this is where we are going to go. So just for your information, because it's not going to be relevant for the following, we actually have a master clock in the brain, just behind the eyes. And this master clock is also an oscillator, it's a strong oscillator. Again, if you take it outside of the brain, you will still get oscillations. But it's also, it's oscillating, but not at a 24-hour period, not with a 24-hour period. So everybody has a different period, and it actually tells you whether you are a morning person or an afternoon person. So if you have a period that is shorter than 24 hours, you are a morning person, and if your period is longer than 24 hours, you are an evening person. And last thing is that basically to synchronize within 24 hours, the master clock uses external stimulus, and in particular the light. The light is the most important one, and basically you have an oscillator with a period of almost 24 hours, and then you force it with the light to a period of 24 hours, exactly 24 hours. And actually, if your whole period is exactly 24 hours, you are very lucky, because it is proven that you live longer. So, because you are more adapted to your environment. Just a fact. Okay, so now let's look back to the cellular oscillators. So this has been known for 30 years or 40 years. And the first guy to actually design a mathematical model of this was again Albert Goldbetter, that we have already seen for the Goldbetter Boltzmann kinetics I showed you, I think, on the first lecture. And it was studied first, not in mammals, not in humans, but in Drosophila, which is a type of fly. So I put a picture of the Drosophila here. So if you take cells of the Drosophila, you have a plot that is rather simple. You will see that the one in humans is a bit more complicated. But here you can see this as basically one protein, which is called pair. Pair is for period. And basically here you have the nucleus of the cell, And then it's transcribed here to get mRNA. Remember that we have seen that here, so we have seen that a few days ago. So you have the amount of mRNA here that we will call M. So this is the transcription. Then mRNA will be translated into proteins. So this is P0. And then you have two steps of what we call phosphorylation. So you can just see this as a transformation. Okay? So transformation of P0 into P1, and then P1 into P2. And then the protein can actually go back to the nucleus with a transport that is in both directions. And then, this is where the interesting part happens. This protein in the nucleus will actually inhibit its own transcription. Okay? So you have activation, inhibition. And this is called a negative feedback loop. Maybe you have heard about it, negative feedback loops. And usually this type of system is actually associated with oscillations. So you can write equations about this, assuming mechanism and kinetics. So then you can maybe ask the question why did they use mechanism and not the law of mass action? Basically, it is proven that if you only have a linear system, you will never be able to have limit cycles. Okay? So linear systems do not have fully linear systems do not have periodic cycles. Periodic orbits. So this is why they have to go in more complex kinetics. So basically, you write the equation for the five variables, and you also assume conservation law. For the pair protein. So here the conservation is for everything but M, because M is an mRNA, it's not a protein. So then we can simulate this. So one handy way to do that is to use Berkeley. I don't know if you have heard about this free software, but if not, I encourage you to actually download it. So it's from the University of Berkeley. And as you can see, there are huge fans of the singer Madonna. This is why we call Berkeley Madonna. And so you can actually very simply program the mathematical models and equations into this software. I can provide you the code, or maybe put the exercise for the mini project to see and then you can then run your system. And for particular parameter sets, this is for instance what you get for the variables M and P0, M the mRNA and P0 the protein in the cytoplasm, with respect to time. And this is something that is close to what I draw actually on the board. So you basically start at some initial points, which are clearly not on the limit cycle. And then, after some time, you actually reach the limit cycle. And then you stay in it. You stay on it, sorry, and that's it. And then you can, so if you use Berkeley, you can actually also plot the phase plane and you see the limit cycle. And you can also use a sliding bars to actually play the values of the parameters. And let's do that. Let's play a bit with the parameters. So now let's say that we have a normal curve and a curve that we call mutant because it's going to be modified for some set functions. And here we say that the mutant will be modified for the degradation rate of pair 2. So I think it's better if I go back to the model. So we are looking at this parameter here. So this is the degradation of this protein. So of course, if the degradation is higher, you will get less protein. If the degradation is smaller, you will get more protein in the system. Okay. And as you can, so let's play a bit with that. So if you have the normal parameter, V is equal to 0.95. If you have the mutant, we set it to 0.5. And those are the results that we get for one of the protein, which is PER2. And I don't know if it's really easy to see, but basically there is a difference in the period between the yellow curve and the yellow curve and the pink curve. And actually, if you measure them, you can measure them just on the graph. You will see that for the control, the period is 24 hours, which is what we want. And for the mutant, the period is 20 hours. Okay. And basically, what it means is that reducing pair degradation shortens the period. And I don't know if that's intuitive for you, but if you go back to here, basically it means that when you reduce that, this will be favored, and basically it will take less time to actually go around one millisecond. Okay? Basically, this is lower, so this is going to be favored. I mean the other arrows. And you are going to need less time to go around the mid-cycle, as the period is going to be smaller. Because I forgot maybe to say that if you go around once for the mid-cycle, in the mid-cycle, it means that you have done a whole period. Okay? You need exactly the time, capital T, to go around the mid-cycle. Okay, and so that's the actual real clock in humans. So as you can see, it's a bit more complicated. So it has actually 2 to 3 loops, negative feedback loops, which are intricated, so they are in between each other. Basically, so here you have 2 compartments. So here you have the nucleus, and so that's the nucleus, and here you have the cytoplasm. And maybe you can focus on one particular clock gene, which is minimal. So every time you have here small letters, it means mRNAs. Every time you have capital letters, it means proteins. So here, everything follows the mass action except the transcription rate. So here I have written, for instance, the equation for this guy, imal1, well, imal here. So as you can see here, you have 3 arrows here. So the idea is to have 1 term per arrow. Well, not exactly, because here we are talking about the enzymatic equation, enzymatic mechanism. So the idea is that basically imal, the mRNA, is transcribed with this rate, which I'm going to explain in a minute, and then it's degraded with this rate. So it's a normal degradation, okay, minus alpha x simple, law of mass action of first order. And it's completely independent of the rest. On the opposite here, this transcription is highly dependent on those 2 guys that we call reverb and ROR. So N is for nucleus. And basically reverb will inhibit transcription of imal, and ROR will activate the transcription of imal. And this is the way that, this is one way to actually model this. If you look at that term here, the transcription term, you can see that reverb here is at the bottom of the term. So basically, when reverb is high, this term is low. On the opposite, ROR is more like a Michaelis-Menten type or Hill type, depending on the coefficient or on the exponent here. And you can see that ROR here, with this formula, will actually increase the level or the value of this term. Okay? I'm not going through the details of all this. This is published here if you want to go and have a look in this paper. And just so the idea of this mathematical model is basically to have a quantitative tool again. So we compare that with the data, and I'm just showing the results here. So here we have data for plenty of different clock genes, not going through the details. Here we have the mRNAs on the first line, second line is our proteins. And we have, so not for all of them, but for some of them, we have actually more than 1 period, which is what you need to really be able to quantitatively parameterize your model. So basically, as you can see, the fit is quite good. If you look at the fit between the data and the model, it's actually quite good. And something else that you can see is that now the oscillations do not look like cosine curves. Okay? You can see some very sharp profiles, sometimes some asymmetry. If you look at this one, for instance, this is not symmetric, and this is really handy because you can actually adapt to your data. So that's it for the mathematical models of the circadian clocks. So I think I will stop here for the models. So tomorrow we will see. I don't know where you so I may go here towards that lecture. So no, let's first. Do you have questions about oscillators? Because here we are going to talk like quickly. So any questions on the oscillator or on the models of the circadian clocks? Yes. How can you be sure that you are talking? For this one, yes. Yeah, no, you're right. Usually it's a numerical analysis. Usually we use numerics. We just run your simulations and draw the baseline. You can use, for instance, XPP code. I don't know if you know this software. And then you don't demonstrate. You just show with your simulations, numerical simulations, that you do see limit cycles. Yeah, you're right for this dimension. I think that's a good one. Any other questions?
Is there any way that we can ensure that the structure that we are writing at the beginning, before analyzing the stability that this system has the very solution?
So your question is, when are we sure that
to ensure that the structure that we are writing at the beginning, of the process of creating the structure that the system will be. How can we ensure that? Suppose that we are interested in a system that explicit is very behavioral, like this one. How do we ensure that?
The question is, how can you design your model so that the structure that the exists is set up?
At the beginning, before analyzing the stability.
So if I understood correctly, the question is how can you be sure from the beginning that you will have a limit cycle which is stable? So how, and I think it's a really difficult question, especially when you have large models. But you have some patterns that are associated with such behavior. For instance, the negative feedback loops, most of the time, they give rise to such limit cycles, stable limit cycle. But you also remember that most of the time when you have a limit cycle, you also have verifications. So anyway, it really depends on your parameter values. Yeah, it's a set of parameter values that you have to define anyway. Yeah. Any other questions about this class? Yes.
I'd like to ask.
You know what to say?
I'd like to ask the perspective in the biology aspect. Circadian rhythm is highly influenced by light exposures, am I correct? So if these oscillations also would in the equation depicted, I'm just curious if how these oscillations in perspective of light exposures, because there are genes that are activated by certain exposures to light, and that degree of inhibitions affects the oscillations pattern.
Yes, so So this is a really good question. So here, this mathematical model, the one I showed, the last one, and actually the one before, is for cells. So here we are not talking about the light, because anyway there's no light sensor in those cells. But then you can extend this mathematical model to account for the light in the case where, for instance, you want to model the plug, the master plug that has sensitive to the light. In that case, you would put, usually you put an oscillator, like a forcing function as an oscillator, that is the light. And then we know that the light actually acts on some of the proteins. I mean, this is known, but a few of the proteins are actually synthesized by the signal from the eyes, the nerve from the eye. And you can actually study that. And then you can show that, for instance, if you put jet lag in your forcing function, so if you change the period, or if you change, sometimes you can say you shift your light by 1 hour every day, or by 2 hours every day, and then you can see how this is completely changing your plug. And which is even more interesting is when you model not just one cell, but plenty of different cells with heterogeneity. And what you will see is that basically you need some time for the cells to go, let's say that you want to get jet lag. So you go from one light exposure, so one like this, and then you shift the plate to say, okay, I'm learning, for instance, for myself, I travel from Paris to Bangkok. So I first run my model with the Paris light, then I take myself, I stop myself here, and I change the forcing function the light of Bangkok, and then you will see the cells that will change or shift to the new regimen, but with different speeds, depending on the heterogeneity that you put. And at the end, you will still get a nice regimen, depending on your system, but most of the time you get a coupling, a synchronization of your cells in the new light, but this takes some time. And actually, we think this is why we are not really good when we are recovering from jet lag. It's because the different cells of our body and the different organs are not recovering at the same time. So you have a desynchronization between your liver, your intestine, your heart, your brain, which is not the original scenario that you want to feel healthy. And it takes a few days, well, for some people actually a few weeks, to actually go back to timing system that is nicely or in its optimal state.
More question? Some more? Okay.
Again, I have if I may say because if I say that degree of oscillations, if it is almost, assuming that the system is functional, it will have its own properties. And if this kind of regularities and these oscillations will have a trend of normality, then you could be able to use it to some kind of a reference. And if there is some sort of abnormality also might indicate something. That's what I thought about the lecture about light exposures. So when the interesting part is if you are in jet lag, what will be the behavior of those oscillations? Something like that.
Yeah, so that's actually really relevant in the field of cancer, because we know that the tumor, they don't display very nice signal results. If you look at this in tumors, you will see oscillations which are not as good as the ones that you can see in the normal cells. Usually the amplitude are smaller, and which may be due to just a smaller amplitude in all the oscillators, but which may also be due to the fact that the cells are completely synchronized between each other. Because in the healthy situation, the cells are supposed to be synchronized. All your liver cells, for instance, the same cell type, you have the same clock. And this is because the body is actually entering the cells. So, but it's not just the first thing you said is that the system has its own behavior, but this is more like a forced oscillators. So you really have to say that anyway, it's not just something something like a dynamical system that is independent to some oscillator or this type of model, you do have a forcing function that is going anywhere that is acting on that as well, I mean on the oscillator as well.
More questions? Okay, thank you.
So I will only introduce the next part and we will do it tomorrow. And then I have an advertisement to do. So now, okay, here this is an introduction to PKPD, okay? So 24-hour rhythms are all in the biology, but we want to go to the pharmacology part. So I'm going to show you one example of an experiment in mice. So here is the experiment. So you have your mice, and the mice are subjected to 12-hour light and then 12 hours of darkness. Okay, so they are in normal conditions. And then you give one drug, which is called oxaliplatin. This guy here, oxaliplatin, to the mice, and you keep the same drug for all mice. The only difference is going to be the time of day at which you are going to give the drug at. So if I draw the clock, or not the clock, the time. So basically you start at 0, you have the light, and then at 12 hours you switch to the dark. And then you continue this, okay, for several weeks. And then you decide to give your drug at different time of the day. Same dose, okay? Same dose. And you actually do this for 6 different timings. And then you look at the survival of your mice over time. So this is time following the treatment of last drug, LOHP, oxaliplatin. And here on the y-axis, that's the survival of the mice. So anytime you see a jump like this, it means that a mouse has died, basically. And the different curves are for the different timing here, which are written here. Halo is for hours after onset, after light onset, hours after light onset. And as you can see, if you give the drug here, so 15 hours after you switch to the light, so you are around here, okay, 15 hours, about 25% of your mice die, and 75% of your mice stay alive. On the opposite, if you give the drug around here, then it's the exact opposite, okay? So 25% of the mice are actually live, and 75% die. And this is just changing the timing, okay? Nothing, no dose change, just the timing. And this is what we call chronotoxicity. Here we are looking at toxicity because the mice are actually dying. And the toxicity is dependent on the time of administration throughout the 24-hour span. Okay? And just to convince you that this is not just for this drug, you can actually do this for plenty of drugs. So all these drugs here are tested in the same way. And if you look at this scheme, just look at the cryptogram. So this is like a graph. From 0 here, and then 24 hours, with the day here of the mice and the night of the mice. And one pictogram means one bug, which are listed here. And they are placed at the best time of tolerability. So for instance, if I go to oxaliplatin, this one I just showed, so this is around here. And the 15, the allo 15, is the best one. so the time when you want to administer the drug at. And what you can see from this plot is you have several things to deduce from this plot. So first of all, there is not one good time that would be correct for all the drugs. Okay? If you look at the distribution of the best timing, they are all over the place. Okay? They are all over the 24-hour span, and you cannot say that there is one particular best timing for every drug. This is not true, and you need to go in more details. And the second thing is that even the family of the drug does not predict the optimal timing. So for instance, if you have a look at this family, the topoisomerase inhibitors, so you have two drugs here, Silpakorn and methoxantone, but you have another one here, this is methoxantone, and you have two here, okay? So basically it means that this is a complex problem. And also for this, the clinicians may need our help to try to model the mechanisms that actually are behind this type of results and this type of difference related to the 24-hour time. I think I will stop here because I don't want to go into too much detail. I think we will be done in the time. So first of all, I will take questions about this tomorrow because I want to talk about too much enough. I would like to finish my lecture just with another announcement, which is that we are actually looking for postdocs. So if you are interested, please come to me. So in more details, so we have in my lab we have two postdocs opening. So one is in biostatistics, which relates actually to this field, which is to look at the timing of some cancer drugs which are immunotherapies, so therapies that are targeted to the immune system. So this is a fully funded 3-year program, 3-year position. And we also have another program which is more flexible, in which you can have funding for 1 year, and then we apply together to other grants during this year, mostly in France, for additional funding. And with this type of program, we can actually design a project together. So this is it. And then two other teams in my unit are also looking for postdocs. The team of Emmanuel Barrio is looking for a postdoc in machine learning in the context of lung cancer. And the team of Florence Garelli is looking for a postdoc in bioinformatics and single-cell analysis. So if you are interested in any of these positions, please come to me. And I don't know if there are master students here, but we also have, there are some PhD studentships that may be available. For sure, there are actually two in the team of my colleague Angelique Stefanou, who is the one who did the hybrid spatial model, the one in 2D with the temozolomide. So with the PD and the grid and all that. So they are in Grenoble, in the south of France, and they have two open positions. So one is in collaboration, so PhD position, here, PhD position. So this is where if you don't have a PhD position and you want to start a PhD. So one is in collaboration with Paris, and the other one is in collaboration with David Poatil at the University of Swansea in the UK. And both are in the context of brain tumors, and both will involve hybrid models using PDs, special PDs, and ODs for the cellular purpose. That's it. So please come to me if you are interested. Remember that we meet tomorrow after lunch.